Eric, we're streaming live to YouTube right now. I just want you to know that. How are you?
I'm very well, Susan, and how are you doing today?
I'm doing well. It's very sunny here, even though it's February, so that's nice.
Oh,
Um,
we have weather in the 50s. It's like spring in New York. Springtime in New York. You should come north.
all right. Eric, my question for you today is I've heard you talk about gravitational waves and how a lot of us think that gravitational waves are unlike other waves or other things. And what do we have? What are we missing in your from your perspective when it comes to our ideas about gravitational waves?
Well, I'm so glad you asked me that question because I've been agonizing over this one for a long, long time.
Uh,
And the answer is like the answers to a lot of questions are really quite simple and straightforward once you figure it out. But they are anything but simple and straightforward until you do. Let me explain why we have this hang up on gravitational waves in the first place. Number one, gravitational waves exist. There is no question about it. They have been detected and they look like nothing else that has ever been detected. That's a given. Now, why don't they look like anything else? uh, that and the one thing that everybody seems to overlook is that gravitational waves are, are waves, and they must. There's only one way of propelling. In fact, I'm sorry. Gravitational waves are the result of propelling particles. So gravitational waves are the result of particles because there is only one propulsion system in the whole universe. It is the structure of the universe itself. There cannot be two separate propulsion systems. So if they're propelled by the same system, why are they so different? And they are so different. Well, we have to go back to something that we established in a previous YouTube session, and that is that the idea that there is an electromagnetic wave is an illusion. There are electromagnetic bursts that occur every time a cosmic node propels a particular particle through the cosmos. And since the particles are roughly spaced the same distance apart, so you get a burst, and then you get a burst of this exactly the same thing because it's the same particle a little time later, and the burst again a little time later. And it looks like it's a wave traveling through space. In fact, it has the lovely title of a traveling wave, and I love that name. It sort of brings back, memories of travel to exotic places. Well, it isn't a traveling wave. And in fact, there are no waves because there is no explanation for how any wave could propagate through the space, nor is there any reason to believe that they do, and they don't. What is happening is that as a particle of, say, light traverses the universe, each time it comes to a cosmic node, it gets another impetus of energy, which drives it forward, and the recoil is an electromagnetic burst. And it is this sequence of electromagnetic bursts that we are seeing, and we believe it is a wave. In fact, Maxwell and Faraday said, okay, it's a wave. What else could it be? It's a wave of light. Well, it isn't a wave of light. It's a set of bursts coming from cosmic nodes. And there was no way for Maxwell and Faraday to have any idea of that at the time that they made this reasonable conclusion, but it's wrong. It never was a wave, and it isn't a wave. It is a burst. Now, why are these bursts different from all other bursts? Because these bursts are not associated with the propagation of anything from space. you have this detector that has been set up. And what gravitational waves are particles of increasing mass energy that cascade onto this system, which measures their impact. It's called LIGO, or light interferometer, something or another. And it has been detecting them, and we know the structure of them. And what it is a number of bursts that keep getting higher and higher in mass energy. And as they get higher and higher in mass energy, they appear to be increasing in the frequency associated with a burst. But since it is not anything associated with the travel of anything, that is what makes them different. And the reason that we cannot detect them is very simple. They are not three-dimensional. If they were three-dimensional, they would interact with other three-dimensional particles, and they don't. So people are quite right in assuming that these are different because they don't interact. But there's a very simple theory of why they don't interact. They're of a different dimensionality. And whereas we can recreate three-dimensional particles, everything from radio particles through light to gamma, particles, we cannot recreate a four-dimensional particle because these are particles that come up from kinetic energy. In other words, the particles that we're familiar with are thermal particles. They come up from the fusion of two elements in the sun, for example. Hydrogen fuses into helium, and in doing so, there is excess energy that's got to be got rid of, and we get rid of it in terms of photons of light and other things. When two huge stars or dark holes collide, you have a loss of kinetic energy. And that loss of kinetic energy has to be gotten rid of. And it's gotten rid of particles that I've called kintons, kinetic energy particles. But since they are four-dimensional, they don't react with anything else, and they are truly eternal. Light can be absorbed by anything. Radio waves can be absorbed by antennas, etc. Kintons cannot be absorbed by anything else, since we cannot reconstruct how two black holes come together in the laboratory, thanks heavens. So, and this is why they are in fact completely different, but the things that we are observing are electromagnetic bursts. It cannot be an electromagnetic wave because it would not make any sense. So everybody assumes it's something different. Well, it's not. They are bursts of electricity, bursts of electromagnetism, and we have shown that within the eye, they have to be bursts of electromagnetism, or the eye would not work in the manner that it does. And this cannot work. Now, there is a way of proving that, and that is a very simple one. We have talked about the dimensionality gap between the 4 dimensions of Einstein and the 6 dimensions of string theory.
Yes.
Now, a fellow by the name of Theodore Kaluza close the gap, and we will talk about this in another session, by saying what would happen if Einstein did not assume space to be in effect 4-dimensional particles, but 5-dimensional particles. Well, guess what happens? His equations relating to gravity hold, they're not affected, but you also get the bursts, the electromagnetic burst released by the cosmic nodes as they propel these bursts. Now, there is no propulsion going here. What is happening is, as these things come together and they merge into one, the mass energy of the particles being being expelled get higher and higher mass energy. So what happens is on the LIGO frame, it looks like a very wide wave and a very, very narrow wave until it impacts. And it is exactly below the radio range in the universe. They are electromagnetic bursts. They are not anything exotic. There are no waves. They are only particles. And the burst that you're seeing is electromagnetism, but it's in the form of bursts. It cannot be in the form of a wave, just like electromagnetism can not be in the form of a wave because the eye wouldn't function if it were. Now, that's a rather long-winded explanation, and it takes a whole chapter to really lay this out in detail, but that I am quite confident is what is actually going on. And it is one more example where the problem that we had in believing space to be smooth and continuous gets in the way of understanding what is going on in the cosmos. We see it over and over and over again. And that is really the whole gist of the book. We need to take a fresh look at the cosmos.
And I think you've said, and look at the cosmos on its own terms.
Exactly.
Rather than in human terms.
Not in human terms. And if we have to, in order to do this, we have to use not units that are used on the Earth because they are meaningless in the cosmos, but there is a cosmic set of units. And it's just like, in order to really understand how a computer works, you have to think like a computer. The universe is actually very much like a computer network, and you've got to understand how the network works, and you've got to think it through in terms of that, and not anything we bring from our very, very limited experience on this tiny little planet of ours. We are a little speck in the cosmos, and if we were gone, nobody would notice it. That is putting ourselves in our place. On that note, I think we can end this session.
On that humble note.
On that humility.
Thank you so much, Eric. It's great to see you.
You're very welcome, and it's always lovely to chat with you.